Welcome back, AP Stat. This is more or less an addendum to Chapter 26. We're going to be talking about how to interpret computer output for a regression model and answer a couple of questions about regression models given computer output. So researchers in food science studied how big people's mouths tend to be. They measured mouth volume by pouring water onto the mouths of subjects who lay on their backs. Unless this is your idea of a good time, that sounds terrible. It would be helpful to have a model to estimate mouth volume more simply. Fortunately, mouth volume is related to height. Mouth volume is measured in cubic centimeters and height is measured in meters. The data were checked and deemed suitable for regression. Let's take a look at the computer output to answer these questions. So here comes number one. Looking at the row that details the slope of the regression line, what does the t ratio, that is the t-test statistic, of 3.27 and the p-value of 0.0018 tell us about this relationship? So what are we referring to? Well, we are referring to specifically for the height. This is going to tell us about the slope of the regression line, which is the hero in analysis of regression. We see this t-test statistic of 3.27. We also see a p-value of 0.0018. All right, so that's where we find these in the computer output. Now, what do those mean? The t ratio, that is the t-test statistic, this 3.27, means that the slope of the regression line for the sampling data is 3.27 standard errors of the sampling distribution of B1 above a slope of 0. Okay? The p-value means that assuming beta 1 equals 0, that is the null hypothesis for inference involving the slope of the regression line. The odds of getting data with a slope like ours is 0.0018. So if it's true that there is actually no relationship between the variables height and mouth volume, if there's actually no relationship, the odds of getting a regression line with a slope like ours is very, very small. All right, let's look at the next question. How does r squared, which is the variation of mouth volume accounted for by the variation of height, help our understanding? The r squared value, often called the coefficient of determination, or what our textbook calls the variation accounted for, how does that help us understand some more details about our regression analysis? So the r squared value, which we find right here, 15.3%, 15.3% of the variation in mouth volume, that's the y variable, is accounted for by the variation of height. The other 84.7% of the variation is due to other factors or simply due to chance. Okay? So combining that with what we learned in question 1, this means that though beta 1 is almost certainly not 0, we can be almost certain that there is some kind of substantive relationship between height and mouth volume. Most of the variation in mouth volume is not accounted for by the change of height, which should give us a little pause. It limits our ability to use height as a predictive tool for mouth volume, all right? Is it a helpful predictive tool? Yeah, but there are limits, all right? A lot of the variation in mouth volume is not accounted for by height, and so we need to be careful there. All right, question number 3. What does S sub E mean in this context? All right, so where's S sub E? You'll see an arrow right here. It points to this S right here. The S should be understood as S sub E, which we know to be the typical residual size. The typical residual size. So what does that mean in this context? The typical residual size for the least squares regression line is 15.66 cubic centimeters. Those are our units for mouth volume, which means on average, the least square regression line's predicted mouth volume is 15.66 cubic centimeters away from the observed mouth volume, given the same height. All right? So for a particular height, how far off is the predicted value going to be, the predicted value for the mouth volume going to be than the actual mouth volume? Well, on average, it's going to be 15.66 cubic centimeters away, all right? And last question. What does the standard error of the slope mean in context? All right, so this is probably the most interesting part, the standard error of the slope. So if we were to look at our computer output and we were to go down here to the variable height, all right, so this is going to talk about the slope of the regression line. We have a slope right here, which we can see in our regression line right next to height, but we also have a standard error, all right? We have a standard error for this coefficient. Now, what on earth does that mean? Well, we did introduce this in chapter 26, part 2, all right? And let's see what it means in this context. In repeated sampling, so after many samples, the slopes of the regression lines used to predict mouth volume are going to vary, all right? So every time you sample, you're going to get a slightly different regression line that has a slightly different slope, right? Even if the data generally do form a pretty nice, neat, linear shape, there's still going to be some variation from sample to sample. That's just how sampling works, all right? So the slopes of the regression lines to predict mouth volume would vary with an estimated standard deviation, that's what a standard error is, of 18.77 cubic centimeters per meter of height.